Good evening, everyone. Welcome. Thank you for coming. We are so excited to have you here back in person. This is the first time that we have done one of these astronomy presentations in person since the early spring of 2020. So we are so pleased to have you here. Tonight, I would like to introduce you to Professor Joe DalSanto. He has always had a deep love of astronomy and has enjoyed teaching it for nearly 20 years. Since joining COD in 2012, he has also authored an astronomy textbook, 2 lab manuals, chaired the Earth Science Department since 2018, and recently led the development of our virtual reality and immersive visualization labs. His greatest joy and satisfaction has always been sharing astronomy with his students, both in the classroom and in public. Please welcome Professor Joe DalSanto.
Well, thank you, Julie, and good evening, everyone. It is good to be back, isn't it? I know a number of you attended our Zoom presentations. I want to thank you for that, but nothing like being back here. I've got quite a topic tonight, and I couldn't possibly tell you everything there is to know about Earth in 1 hour, but I will do my best to give you some interesting information to enrich your understanding, maybe pose a few more questions in your mind, help you appreciate more our magnificent home, the Earth. I just thought that after doing so many presentations on the universe, let's come back home and pay a little due to our Earth. So here's what I've got in mind for tonight, kind of 4 major sections. Number 1, I want to talk briefly about Earth's formation, talk a little bit about its geologic activity. You'll see the importance of that and how that's affected the Earth, what that's done to the Earth. We're going to talk about the processes that shape its surface. And you'll see some familiar things that I hope will be in a new light for you. Then I especially want to spend some time on the cycles of Earth and how they enable life. That's obviously a very important topic, isn't it? How is it that Earth has been able to maintain life for such a long period of time? Most of its history, much of its history, I should at least say. And finally, that last one you can see, I just couldn't resist because I know there's going to be questions on that one. Could there be other planets like Earth out there? Well, we'll get to that and we'll discuss it. And at the end, of course, as always, I'll invite your questions. Okay, so let's get started. We'll jump right in. How did Earth ever get here? Well, to answer that, we've got to talk about how our solar system got here. I've touched on this briefly in other lectures, but basically, we have what we call the nebular theory of our solar system's formation. Out in space today, we can see enormous clouds of gas and dust. Our solar system began from one of those. Slowly, gradually, gravity takes a cloud like that and begins to contract it. And that contraction continues over long periods. You can see 3 things that are going to happen to this cloud as it contracts. It's going to start to heat up, especially in the middle. Why? Because these particles, farther from the center, are going to be drawn inwardly by the gravity of the cloud. And as they begin to speed up or accelerate, that is equivalent, roughly speaking, to thermal energy or higher temperature. You can probably guess in the very center, of course, is where it's going to get the hottest. That's going to turn into a new star like our sun. The cloud is also going to slowly begin to spin faster. Why would it do that? Well, I like to use the example of ice skaters. You've probably seen ice skaters on TV. They go skating down the ice. They go into a spin. They put their arms out at first, don't they? But what happens when they pull their arms in? They spin faster. Why? Well, the technical reason for this is called angular momentum. They have a certain amount of this, and as their arms are pulled inwardly, their size, or you could say kind of their diameter, gets smaller, and therefore they spin faster. This happened to our cloud. You can see in the various steps here as this is occurring, the third thing is going to happen. The cloud's going to flatten. Why would it flatten? Think of it this way. If you have the spin axis vertical to you and me, material from above and below, of course, can fall easily inward. But material perpendicular to that spin axis is going to feel an outward pressure from the spin. Think of it as centrifugal force. and so our cloud's going to flatten. So this is admittedly a very simple description, but I think it gives you enough to see that our sun would form with a flattened disk of material around it. In that disk is where the planets are going to form, including Earth. Okay, so now let's take the next big step as far as Earth's formation. How did Earth form? Earth formed in the sense that this material in this disk, again, made of countless trillions of particles, these little particles begin to stick together. And they get a little bigger and a little bigger and a little bigger. And as they do so, they begin to get big enough that they have just a little bit of gravity themselves to pull in more particles. And they get bigger and bigger and bigger. As they reach a few tens of feet, hundreds of feet perhaps, we begin to now call them planetesimals. They're not planets, but they're not really particles either anymore. Okay, and we'll come back to those a little bit later. Well, as you can kind of see here in the various diagrams, those planetesimals can also begin to collide and stick together and get bigger and bigger and bigger, eventually growing into a planet. Again, an admittedly simple explanation, but I think you get the point that this is how planets grow. And as you can see there in the top animation, the various stages in this, how that disk gradually changes into planets. You can already see in part of that some gaps in the disk where the planets are drawing in material and growing in size and mass. By the time you move through those other stages at the bottom left over to the bottom right, you can see now your planet growing, and there's still particles, still planetesimals being pulled in, crashing into it, increasing its size. So picture now roughly 4.5 billion years ago. This is what was happening in our solar system. Planets were forming, and you see the term there we use, accretion. Accretion is what basically forms planets. So that's a very quick explanation of how Earth began. Picture it as it is there in the lower right, initially very hot. We're going to go on now and talk a little bit more about the interior of Earth. After this initial formation, this accretion, the outside of Earth would begin to cool, forming a solid crust. But there was still a tremendous amount of heat inside, and most everything inside is still in a liquid format. Here's where early on, denser material can begin to migrate towards the center. Gravity is going to pull the denser material more strongly than it is the lower density material. That's going to gradually migrate towards the surface. You can see the result here. The Earth is going to separate inside into major regions, 3 major regions. That rigid crust on the surface, that large orange region you see there, we call that the mantle. And that grayish region we're going to call the crust, where the densest materials are. You can see some of the composition there. Metals, particularly nickel and iron, are going to get concentrated in that core. The mantle is more of a medium density, things like silicon and oxygen. And the crust that you and I walk around on technically is the lower density material, made of other different minerals and elements, such as granite and basalt. So again, a very simple explanation, but I think you get the point that it's very important for us to understand that Earth's interior is segregated into these regions. Differentiation is the term we use for this. The interior of Earth is differentiated into these 3 regions, and we're going to see the importance of those as we go along now. Okay, so we're getting our first good idea of how Earth got here, how it began to change early on. Now I want to talk about geologic activity, things such as volcanism, earthquakes, other activity that the Earth undergoes. First of all, why does it do that? Well, the short answer is that there's all this heat inside Earth. There's all this energy. I'll get to why in just a second. But look closely at this diagram. What we're trying to illustrate here is that this heat, particularly towards the center, is going to cause hot rock to gradually rise towards the surface. As it contacts that underside of the crust there in particular, it's going to be able to transfer some of that heat, a little bit of which can radiate to space. But now the rock, as it cools, descends back down. And you can see in the diagram behind me, we get these huge cells. We call them convection cells. Now this takes a long time. Okay, this takes a long time for this rock to move like that. But you can think of it in the sense that it is taking heat from deep within the earth near the core, transferring up towards the surface more. Again, this can take millions of years, but it's a very slow, steady process. Okay, you can see my next question. Well, where's the heat come from? It's deep within the earth. There's several different ways that Earth has made heat. Let me start out by describing its heat early in its history, and then we'll get to today. So early in Earth's history, we just finished explaining that a lot of large objects were crashing into the Earth. Now, any large object moving has a certain type of energy we call kinetic energy. It's energy of motion. And when it crashes into the Earth, that energy has to go somewhere. It's essentially going to change into thermal energy or heat. In other words, these impacting planetesimals generate heat in the young Earth and really the other planets as well. This happened, of course, early in its history. Today, we don't really have this happening. Things aren't really crashing into Earth very often, are they? We also mentioned differentiation, didn't we? This is a much slower process, but look closely at the diagram here. Notice the gray drops falling towards that center, as we talked about the higher density material. Even though they're moving very slowly towards the center, you can still think of them as having a much greater, what we call potential energy, farther from the center. And as they fall inwardly, that potential energy must be changed into thermal energy. So there's a net gain here of heat as well during the period of differentiation. Well, after many, many millions of years, this has pretty much established what we just saw on our previous slide, that Earth is separated into these regions. So that process is not taking place too much today. But notice our third one here, of course, radioactive decay. Earth is stocked with a tremendous amount of elements deep within it, some of which are radioactive, and you might know that radioactivity generates heat. And this is the primary source of Earth's heat today. It has continued on for many, many millions of years, continues to supply this heat deep within the Earth, near the core and throughout the mantle. This is the current source of energy that we've been describing to drive that heat. Now, you'll hear me use the term heat and energy somewhat interchangeably. They're not exactly the same, but they're similar enough for our purposes tonight. So this gives us, again, our first good look not only at the structure of the Earth, but how it got like that through this, these steps, rather, of generating this heat. Okay, so now we picture our Earth after its formation. It's gone through these processes. I want to emphasize the importance of the fact that as far as rocky terrestrial planets like Earth, Earth is the largest one in our solar system, and that means it has a tremendous amount of heat within it. Other worlds are not so large. Notice here on our diagram, we have the moon at the bottom, we have Mercury, even Mars. They're not as big as Earth. It turns out if you do the calculation to compare really the ratio of the volume of a planet with its surface area, you find something interesting, and that is that the smaller the world, the more surface area per volume it has. In other words, that surface of that world can radiate the heat away, and this world will lose its internal heat faster than a larger world. This is why the moon and Mercury long ago lost their internal heat. They've essentially radiated it away. They didn't have the huge reserves that a large planet like Earth has. And so inside, they're not nearly as hot. There's not nearly the amount of energy. And so as we're going to see, they're geologically dead, essentially. They really don't have much geologic activity anymore. In contrast, Earth, almost certainly Venus, being much larger, that ratio is different. They have a larger volume per surface area, and therefore the heat is not escaping as quickly. And therefore they're able to hold on to more of that heat, more of that energy to drive geologic activity. So on our graph here, you can kind of see those arrows illustrating this. Mars is an interesting medium-sized planet, and that puts it right in the middle. And what they're trying to illustrate here is that Mars was geologically active for some time, but now that's gradually faded away. Just recently, NASA landed a spacecraft on Mars to measure that heat flow, and they pretty much confirmed our picture here. That again, long ago, Mars would have had a lot of heat inside, a lot of energy, but really no longer. So interesting how already we see an important factor here, that Earth being a large planet has kept it geologically active until our day. There's one more piece I want to add to this that's more important than we might think. That metal core of Earth that we described is exactly that, made of metal. It's very hot, it's liquid in general, and it's churning. It's moving with all of that energy. And the Earth, of course, is also rotating on its axis. So that metal is in motion. And anytime you can put metal into motion, you can generate an electric field. Anytime you have an electric field, you can generate a magnetic field. We probably all know Earth has a magnetic field. Years ago when I was young, we'd walk around with a little compass and you could point your way north. Today we usually pull out our phone instead, don't we? But the point being, we're probably all aware, yeah, Earth has a magnetic field, and that extends out beyond the surface. It makes a region around Earth we call the magnetosphere. That magnetosphere is very important in many ways. Number one, it protects not only you and me, but our atmosphere from the sun. The sun, of course, gives off light, gives off heat of different types, different wavelengths, but it also gives off what's known as the solar wind. The solar wind is charged particles, and those charged particles would severely damage our atmosphere, besides you and me, but that magnetic field deflects most of it. Sounds pretty nice, doesn't it? Well, the point being is we're going to see later on not all planets have that, and as a result, they don't have the protection of a magnetic field, do they? You can see in our little animation here the aurora borealis. I don't know if anyone's ever had the pleasure of seeing that. I always think that's a little reminder to us. A little bit of the sun's energy there, a little bit of that solar wind's leaking through the magnetic field near the north and south poles, crashes into the atmosphere, and that energy excites the air molecules to glow. And we see this beautiful display. Well, it's again a little reminder, our atmosphere can handle a little bit of that, but the point is that's a way to visualize the fact that Earth is, again, being immersed, so to speak, in this energy, in this solar wind. For the most part, we're well protected by our magnetosphere. So keep that in mind as we come back to that in a few minutes here. We'll talk a little bit more about the importance of that. All right, we've now again established, I think, a real nice understanding of the formation, the interior of the Earth. Let's now move on and talk about the surface. There's three major processes that I want to talk about that have really affected the Earth over its history. Very early in its history, of course, you can imagine objects crashing into it. We're making a lot of craters, right? But these three processes you see here have pretty much erased those craters. They've changed Earth's surface. There's very few areas on Earth where the surface is really, really old. There's a few left, but not much. These three processes have made those changes. So let's talk about each of these. You can see obviously here volcanism. Probably seen pictures of volcanoes. Erupting hot lava, right? A lot of energy there, a lot of heat. We'll talk about tectonics. What's going on deep within the Earth that affects the surface? And we'll also touch briefly on erosion. We know that's more of a weather-driven process. That can change the surface dramatically. So let's go ahead and talk first about volcanism. First of all, no surprise, it requires a lot of heat. We just talked about that, right? Earth has a lot of heat, and that manifests itself. You can see here kind of a classical diagram. The rock is molten. Different areas are going to have more or less pressure. You get an area with enough pressure, it's sooner or later going to burst through the crust. And we can sometimes get a very explosive event, lava flowing out, okay? But the point being, again, that this will gradually and dramatically change the surface, certainly in the immediate area, but we're also going to see how this will affect Earth globally. It's not only that immediate area that volcanism affects. So again, you can see in our diagram here, on Earth, generally speaking, the lava has a certain consistency, although there's some variations. It tends to build those traditional, familiar cone-shaped volcanoes that we see in various areas. And we know that area then is particularly volcanically active. Our area is not here in Chicago, so that's a good thing, obviously, okay? A second very important factor that is often overlooked is that volcanoes not only emit hot lava, liquid rock essentially, but gas. We're going to see later on this is really important. Various gases such as water vapor, carbon dioxide, and others are emitted by volcanoes in significant quantities. And one of the things I'd like you to remember as we come back to it in a few minutes is that this has gone on throughout Earth's history. And this has had dramatic changes in Earth throughout its history. There have been times when it's been more volcanically active and the time when it's been less. But overall, this process has had a long period of activity, really since Earth's beginning, and it has dramatic effects on Earth. We'll see that in just a few minutes here as well. Let's move on to tectonics. Tectonics really deals more with what's happening deep beneath the surface and how it affects the surface. Okay? Look down to the lower right there, you see a little animation showing again how some hot rock can move upward in a certain area and spread apart. Other areas it is cooled, falls back down. We talked about this, right? Convection. Look closely. In some areas you can see it's illustrating the little arrows are underneath the crust and moving it in a certain direction. In some areas, these are pulling apart the crust. And you can see that over on the right. The Red Sea is a good example of this. There's been tectonic forces beneath the Red Sea pulling that apart and giving us a deep valley. It's, of course, filled in with water at this point in time. But over on the left, we have something very different. We have a region where the material beneath the surface is rising and pushing the crust together, essentially pushing up mountain ranges. The Himalaya mountains are the classic example here. We're going to talk in just a minute about how this has occurred in more detail, but India, that whole subcontinent, is crashing up into Asia, and the crust is responding by being forced upwardly. The Himalaya mountains are getting taller. So if you want to climb Mount Everest, don't wait. It's only getting taller, about 1 inch per year, so, you know, when you can get over there. So this is a dramatic evidence, isn't it, of what's happening beneath the surface. We see what's happening on the surface, we can interpret it and understand what's happening deep below there. So we have these two classic examples where the crust is pushed together or it's pulled apart. Sometimes the crust can also slide sideways. We see that, for example, in California. Maybe you've heard about that region where different areas of the crust are pushing sideways. That can also be an area of geologic activity. Okay, so this is the basic idea behind tectonics. Again, deep within the Earth or deep within any planet, you can have this. We strongly suspect, I'll just quickly mention as an example, Venus shows some signs. It's a little different example that I won't go off at the moment. But any planet in general could experience this to varying degrees. Earth has its own special version of tectonics that we do not see on other planets. That's called plate tectonics. Maybe you've heard this. The surface of Earth, its crust, is not one continuous piece. It's broken into these plates, as you can see on the right here. Those red lines are showing you where the boundaries between the plates are. You can bet those are areas of geologic activity in one way or another. So again, we now visualize the tectonics deep within the Earth coming up. These plates are being pushed in different directions over time. And again, it's a very slow process on the order of perhaps 1 centimeter or 1 inch per year, something like that. But you add that up over millions of years. Millions of inches add up, don't they? And so the point is, as these plates have moved, you can see down there in the lower left, so have the surface moved. You and I think in terms of the continents have gradually moved. Technically speaking, it's the continental plates that have moved, but the continents are riding on top of those. There's other areas that maybe are not continental. They're moving as well. In fact, if we take the motions that we can measure in various ways and we wind that backwards, you can see what we can get here. We can determine where the plates were in the past, and they looked very different, didn't they? You saw for a minute there how different plates have moved to form Africa, South America. We can literally look back in time and understand how different the Earth's surface. Here you go. Notice that South America and Africa were once close together. Notice in particular, by the way, look to the lower right there. You notice India breaking free and racing upwards, so to speak, to the east of Africa. It's going to crash into Asia. That's what I was describing a minute ago. If you notice again, India over there, right on the very right edge of Earth. So some of these plates move faster than others. They obviously move different directions, but they have dramatic effects on the surface of Earth, the tectonic plates. This is unique to Earth in our solar system. We don't, for example, see this on Venus, even though it's basically the same size as Earth. We think it has roughly the comparable amount of energy within it, but we don't see this there. Why not? Well, the short answer is Earth's water. Earth's water makes a dramatic difference. That water is not only on the surface in our oceans, but it percolates through the crust and, so to speak, lubricates these plates so they can move around. On Venus, there's no water. There's no water, and therefore the crust is rigid, but we see something very interesting that kind of fits here. We'll see places where it sure looks like beneath the surface we have an upwelling of material, but it can't get through the crust, and it can't move the crust. So interesting how Earth's water makes it unique in the sense that it's a major factor in plate tectonics. Well, here's one more animation, a little faster on the upper right. You can see there, during the 20th century, we developed a very solid theory of plate tectonics. It really began almost 100 years ago, about 80 years ago, I think, with a scientist who said, you know, it sure looks to me like the continents kind of fit together like puzzle pieces. He particularly didn't notice South America and Africa, how well they fit. Now, of course, you got to sometimes ignore the ocean water. It's not a perfect fit, but it's very, very close. And since that time, there's been a number of different lines of evidence that support this theory. One that I particularly think is particularly significant is the fact that identical rocks and even identical fossils have been found eastern South America, western Africa. These are fossils of creatures that didn't swim across the ocean and they didn't fly across the ocean, but they're found in both places. Doesn't it make sense that those land masses were joined together and these various creatures flourished during an ancient period of time? Then the continents moved apart. So I think a beautiful example of the type of evidence we can have. We're going to see some more here in just a minute. And as I said more than once, the motions of those plates can tell us the past positions. Today we have the technology to even use our GPS system. We can place very sensitive, very stable markers and literally measure them moving apart year by year by year. We couldn't do that years ago, but there were other ways we did that. We're going to talk about one in just a minute here that helped us establish this theory of plate tectonics. Notice my final point here, though. Geologists found something very interesting when it comes to the Earth's crust. It's not uniform in thickness or age. The seafloor is thinner and younger than continental crust. Why would that be? Usually in class I pause and make a student answer, but I won't make you answer, don't worry. Well, surely there must be a good reason for that, and there is. And here's where, again, a theory can explain. It can help us understand to a deeper level why that would be. All right, here we go. Stay with me now. We're going to talk about something called subduction. What is this? Start with me on the left-hand diagram at the number 1. Out in the middle of the Atlantic Ocean, we have an area where the plates are spreading apart. It's called the Mid-Atlantic Ridge. We've literally sent probes and even divers, I believe, down to certain areas, and you can literally see brand new rock coming up through this. You can get a sample of that, and no surprise, it's brand new rock. That ridge, again, is where two plates are pulling apart. So year after year, as new rock comes up and forms, it gets farther and farther and farther from the center. You can guess what's going to happen. If you were to measure the ages of those rocks farther from the ridge, they get older. They've been above the surface longer. Okay, that makes sense. But anywhere, of course, the Earth's surface is being pulled apart, the Earth is a spherical planet. Sooner or later, if this is getting pulled apart, this has to push together, doesn't it? Well, that's happening over here in step 2. The Pacific plate is moving towards the North American and the South American plate. What's going to happen here? Here's where subduction begins. Subduction refers to the fact that when you get these two plates coming together, the oceanic plate is going to dive below the continental plate. The continental plate is going to rise up above it. Generally speaking, a little bit lower density is going to cause that to drive that oceanic plate beneath the continental plate. Of course, as it gets deeper, it gets hotter. That rock begins to melt. Now that oceanic, or you could say that ocean floor, that crust has material in it that has slowly accumulated, sediments and other things over long periods of time. As that material gets down deeper and hotter, the pressure is going to build. The pressure is going to build, and you know where I'm going here. We're going to get volcanism. We do see volcanism, for example, in the Pacific Northwest, state of Washington into Oregon, where this is occurring. We especially see a classic example of this along the west coast of South America. The Pacific plate is diving beneath that, heats up, we get volcanism along there. There's a chain of mountains along there through Chile and areas of that nature. And interestingly, some of those can move fairly far inwardly, a number of miles inwardly. It's not just exactly right on the edge there. So subduction is going to be a very important process for us here as we move along in our lecture to understand what's happening to Earth. And you'll see in just a few minutes here how important that can be. But this is where you could think of the seafloor being kind of recycled, so to speak. Sent back down, it melts. We get these eruptions, volcanism occurs. Our Earth's a very dynamic planet, isn't it? There's a lot going on. A lot of energy, a lot of activity on the surface. You can get a little animation there on the right of what we've been describing. And again, different areas are going to have more or less of this. But it's a very important process, subduction. Let's look at our third process, erosion. This might be a more familiar term perhaps. Generally speaking, we're talking about water or ice or wind changing the surface. Grand Canyon is the classic example of that, isn't it? Of course, the Colorado River has run through that course now for millions of years, carved out this enormous canyon. We can literally see a lot of geologic history there, of course. But look in our center picture, even ice can do this. It can carve out rock. The Yosemite Valley is a classic example of that. Here in both of these, we're primarily removing material and transporting it somewhere else. But there's other places you can see even the wind can cause erosion. It can transport or move material around the surface of the planet, pile it up in some areas, remove it from others. So now you begin to see why Earth's surface is of varying ages, and most of it is not as old as the planet because it's been affected by these three processes. Erosion is very important as well. Well, we've got, I think, a good idea now of how the surface of Earth can be changed. Let's take just a few minutes, talk about its atmosphere. How did Earth even get an atmosphere? Let's go back to those early times when Earth was still forming. It's going to form with a lot of different elements. Turns out that disk that we talked about, that planets form out, had a lot of different elements. But interestingly, that disk had a lot of hydrogen and helium, the lightest elements. Why? Because that's mostly what the whole universe is made out of, is hydrogen and helium. The sun is mostly hydrogen and helium. So was the Earth at the very beginning, but it didn't take long for those two elements to primarily escape being the lightest elements, it's harder for gravity to kind of hold on to them. Earth lost most of its hydrogen and helium fairly early. Farther out in the solar system, my students could tell you, more massive planets held on to more of that, especially because it was colder out there. In closer to the sun, where the Earth is, the sun's heat helped this process along. So anyway, Earth loses its hydrogen and helium. You've got more denser materials, more rocky type materials. Now our volcanoes begin to kick in. That internal heat starts to drive that volcanism. Remember, those volcanoes don't only give off liquid rock, though, do they? They give off gases, water vapor, carbon dioxide, and others. As Earth's crust now begins to cool, so does the water vapor. Rains begin, and I mean rains. For long periods of time, our oceans gradually develop liquid water. This didn't happen on Venus for very long because of its position, its higher temperature. But the point is, the oceans begin to gradually form. Now something interesting happens. Those oceans have the ability, on very slow process and over long periods of time, to gradually absorb some of the carbon dioxide out of the atmosphere. This began to have a significant effect on Earth from its beginning. Where'd it go? Think of that carbon dioxide as gradually being able to settle down towards the ocean floor. And as other sediments are piled into that, some of that running off of the continents, for example, you begin to build rock on the ocean floor that has carbon in it. Why am I emphasizing that? Because you're going to see in just a second this is really important. Carbon is being taken out of the atmosphere at a slow rate by the ocean and put down into the ocean floor seabed where it forms rock. And that CO2 is now stored there. Well, for one thing, there's less carbon dioxide. That means that the percentage of the atmosphere now begins to tilt more towards nitrogen, which is still true today. We primarily have nitrogen in our atmosphere. Okay. The other big important gas, of course, you're probably wondering, we all like to breathe oxygen, right? Where'd that come from? Turns out we think that very early in Earth's history, bacteria began to slowly generate oxygen in the oceans and elsewhere. Later, of course, today you know that plants do that, don't they? So life began to play a role in changing our atmosphere. Today we know of the process called photosynthesis, right? Plant life takes carbon dioxide, sunlight, gives us oxygen back. That was, of course, crucial for the development of animal life here on Earth, including ourselves. So the point being, you can see again how Earth is slowly, gradually, but steadily changing into a planet that you and I can live on. Interesting how these processes took place over long periods and made Earth more habitable. So that's a very quick primer on our atmosphere. There's so much more. I'm sure our meteorology professors could tell you an awful lot more. But the atmosphere, of course, I bring up not only because it's important for us to be able to breathe, but again, that enables life, not only in the short term, but in the longer term. Let's see how. How does the atmosphere keep us habitable? You've probably heard this term in recent years, the greenhouse effect. The greenhouse effect simply means that certain gases in our atmosphere help to hold some heat in. If you've ever been maybe at some point in time in an actual greenhouse, you know they get pretty warm in there, right? Sunlight can travel through our atmosphere. It's going to warm up the ground. The ground's going to begin to release heat. Normally that would be lost back to space. But these greenhouse gases, water vapor, carbon dioxide, methane in particular, these kind of the big three, they tend to hold some of that heat in. And therefore Earth's temperature is significantly warmer than it would be without those gases. Significant enough to enable liquid water to exist, and significant enough to enable life to exist. I actually have my students calculate the differences. You can see here, for example, Venus and Mars. Venus has a very, very strong greenhouse effect. It holds in so much heat its temperature is several hundred degrees warmer than it would normally be. And so it's so hot there, of course, water can't exist, life can't exist. Mars is the other extreme. It has a very, very slight greenhouse effect, not enough to really even be significant. As a result, once again, the temperature is not changing much at all from what it would be. So in other words, you can again see here that Earth's greenhouse effect is just right for life. It keeps it somewhat warmer, but not so much that it would be detrimental. So the greenhouse effect is obviously very important for life on Earth. Makes us unique in that sense that we're balanced just right there. Okay, so the greenhouse effect, again, provides that extra piece, so to speak, that's necessary. But now I want to talk about how the greenhouse effect remains relatively stable. How is it that life has existed for so long on Earth? How is it that Earth's climate has been stable for so long that life could exist? The carbon dioxide cycle you can see here. What does this mean? Again, I'm going to take you through a few steps, okay? Number one, I'm going to keep this simple. As rain descends, it can remove a slight amount of carbon dioxide from the air. So our atmosphere has a certain amount of CO2. Rainwater tends to do what we call wash that out, so to speak. A lot of that's going to fall on the land. A lot of it's going to fall directly into the oceans. Even if it falls onto the land, of course, some of that land is going to allow that water to flow into lakes and the oceans. It's going to carry with it some minerals from the soil. So basically what we're doing here is we're putting carbon dioxide from the atmosphere into the oceans, and we're adding in these minerals into the oceans. You mix those together, you give them plenty of time to kind of settle to the bottom of the ocean floor, layer after layer after layer after layer. The pressure continues to increase. You start to make that ocean floor crust into rock. That rock contains carbon dioxide, okay? Now you know what happens next. We've already talked about it. Look at our diagram here. That oceanic crust is going to get subducted, isn't it? Not everywhere, but in many places it's going to get subducted deep into the mantle. We described what's going to happen. It's going to heat up, the pressure's going to grow, and sooner or later you're going to get volcanism. We also said earlier that volcanism is not just going to shoot out hot lava, liquid rock, it's going to spew out those gases, including carbon dioxide. So can you see the whole cycle here? Can you see the cycle? Some carbon dioxide in the atmosphere is taken out, some is stored in the ocean, some is put into the ocean floor, some of that is subducted, and eventually some of that is put back into the atmosphere. Now make no mistake, throughout Earth's history, this cycle has varied. In other words, sometimes more has come out or more has gone back in. What's the point of all that? That's a nice cycle. The point is that carbon dioxide is a greenhouse gas. It's going to have a tremendous effect on the greenhouse effect. In other words, if there's more carbon dioxide in the atmosphere, you know what's going to happen to the Earth's temperature, right? The greenhouse effect will be stronger, the temperature will rise. But if there was less, the opposite would be true also, wouldn't it? Let's take a look and talk through that just for a minute. Let's imagine, and it has happened, of course, that over different periods of Earth's history, the Earth has gotten colder and warmer. There are slight changes in Earth's orbit, slight changes in its axis tilt. You've probably heard of ice ages. Okay? During a cold period, when the ice grows, we have less ocean surface, don't we? Think of the polar caps, for example. Now we have less evaporation with a colder temperature. If we have less evaporation, we have less precipitation. If we have less precipitation, we're taking less CO2 out of the atmosphere, aren't we? We're not taking as much out, but meanwhile, the volcanoes don't care. They're going to continue to spew CO2 back up into the atmosphere, and the level's going to rise gradually, slowly. it's going to increase the greenhouse effect and warm the global temperature. Now, admittedly, I'm greatly simplifying, but you get the basic idea, right? Likewise, if the Earth becomes hotter and hotter and hotter for some various reasons, something opposite's going to happen. We're going to evaporate more water. We're going to precipitate more rain. We're going to wash more of that CO2 out of the atmosphere. And we're going to store that in the oceans and in the crust. And if we have less CO2 in the atmosphere, the greenhouse effect weakens, our temperature begins to reduce. Again, admittedly simple, but I think you get the point. This cycle then has kept Earth from getting too hot or too cold. There have been times when there's been a lot of ice on Earth, and there's been times when there's been none. But the point is, this carbon dioxide cycle has kept Earth in a range of temperatures that life can adapt to. It hasn't gotten so hot that life could not exist, or so cold that life could not cope. So the CO2 cycle, I think, is such an amazing thing that Earth has that we probably don't think about much, but it has kept Earth habitable for most of its history. And this has given us a very stable climate. Okay? So let's go back now. We've talked about a lot. Let's take a minute and kind of step back and summarize in our minds what are the big factors that enable life. Obviously, liquid water, that's an obvious one. It begins, of course, with the fact that we're the right distance from the sun, isn't it? If we orbit where Mercury is, it's just too hot. If we orbit where Pluto is, it's just too cold. Okay. So we had to be at the right distance. I'll come back to this later, too. That's an obvious one. The right distance for what? The right distance for liquid water. Venus boiled its oceans away early in its history because it was too hot. Okay. Number two, didn't we see that plate tectonics have something to do with enabling life? Think about it. Plate tectonics enable subduction. Subduction enables the CO2 cycle. The CO2 cycle keeps Earth's temperature within a range. It doesn't get too hot, doesn't get too cold, doesn't it? It kind of moderates the greenhouse effect. Won't let it run away like on Venus. This, of course, then, this moderating of the greenhouse effect provides climate stability. Okay? The temperature never gets so hot or cold that there's no liquid water on the surface. The final piece we mentioned just briefly is life itself has contributed. Early life began to contribute oxygen to the atmosphere. That enabled later animal life, more advanced life, to develop. And here you and I are breathing that oxygen, right? So what a beautiful system Earth has, doesn't it, of processes that all work together to enable life. Makes Earth look pretty special, as we're going to talk about in a few minutes. Are there other Earths? Maybe. But they're going to need to be pretty special, aren't they? Okay, so we'll talk about that as well. Well, at this point, I got to change gears a little bit and talk about a current factor. I'm sure you're well aware of this. I won't dwell on it excessively. But now there's a new factor, isn't there? There's a new factor affecting our planet. It's us. For the last, 150 years or so, we have been doing some things to our planet that have not been good. The one we'll focus on here, as you see, is use of fossil fuels. What do we mean by fossil fuels anyway? Well, ancient life, as it was made of carbon, would die and deteriorate in the lower areas of Earth and essentially turn into these fossil fuels: coal, oil, natural gas, those kind of things. We've dug that stuff up and found out, hey, there's energy there. We can burn that. Oh, that's good, but we are releasing the carbon back into the atmosphere, obviously, in very large quantities. So how do we know this? Well, you probably are familiar with the fact that the global average temperature of Earth has been increasing now for some time. This graph, I think, simply but clearly shows that. You compare the average temperature at any one point to the average from 1950 to 1980, and you see a dramatic change, don't you? The late 19th, early 20th century was below average, but for the last 60, 80 years, we've been above average and we are climbing. Now, 1 degree might not sound like a lot to you and me in any particular location, but you have to think of that in terms of the whole planet. 1 degree planet-wide is an enormous amount of heat. Why is this happening? You can see the answer here. You've probably heard this as well. We now know that the levels of carbon dioxide in Earth's atmosphere have been increasing dramatically right during the Industrial Revolution and forward. And this is what's going on. How do we know that? Here's 2 graphs I want to spend just a minute on. Look closely at them. Basically what we have here is temperature increase at the top, carbon dioxide levels at the bottom. Let's start at the bottom, actually. Notice, first of all, the carbon dioxide levels have changed in the last 500,000 years. In fact, they appear to be cyclic, don't they? There's been decreases, there's been increases, there's been decreases. So Earth, you can see here, goes through these changes. That's not in question whatsoever. But notice also that those changes match closely with the changes in temperature. When the CO2 level rises, the temperature rises. When the CO2 level drops, the temperature drops, doesn't it? Up and down, up and down. Very close correlation here. Okay? Second thing I want you to notice is in that bottom graph, notice how the level of CO2 has varied, but it's varied between 200 and 300 parts per million. This is over 500,000 years. Okay, so in other words, there's a range as we talked about, didn't we? There you can see it. But of course, look all the way to the right. We are now far above that range, aren't we? We just recently passed 420 parts per million. So clearly, this is not a natural variation. If you look closely, you can tell also it's a very, very much faster change. Let me zoom in just a little bit here for you. Just in the last, 60 years or so, we have skyrocketed almost 100 points. So again, it's not a natural change that we're experiencing. No surprise that the temperature is increasing because of this, and we know the reason why. There's only one way that this tremendous increase has occurred. It's by our putting that into the atmosphere. Here's a little different view of what's going on. You see much of the warming in the northern hemisphere in particular. We're taking here a 30-year average. We're going to see in just a minute a couple other pictures that show you what this warming in the northern hemisphere has done. Think particularly about our north polar cap of ice. You can imagine what this increase is doing there. Not quite so much in the southern hemisphere. There's more ocean, not as much land. But the point being, it's very clear what's going on here to our Earth. So what are the consequences? I won't take a lot of time here being negative, except that it is sobering. Number one, we're already beginning to see changing weather patterns. Storms, more intense, more numerous. You probably heard about the glaciers are starting to melt, right? And that's another whole topic, I guess. Not only do some of those glaciers pour water into the oceans, now beginning to raise ocean levels, it's been measured. But other areas, glaciers, people depend on, parts of Asia, they depend on glaciers to bring them their fresh water. When those glaciers disappear, those people won't have fresh water. It's a very serious thought, isn't it? We've also begun to see changes in our patterns, droughts in some areas. Think about the far west now, the Colorado River and those large lakes out there, Lake Mead, their levels are at record lows due to the droughts out there. So we begin to see multiple signs of how the Earth is being affected. You can see a few pictures here of glaciers disappearing. Here's those polar caps I mentioned briefly. And one other point here I'll make just quickly. You notice the change here, of course, as the polar cap is shrinking, right, from decade to decade here. Those polar caps, being of bright, fresh ice, reflect a lot of the sun's heat back to space. But as they shrink, they reflect less heat back to space. Those darker, warmer oceans begin to absorb more heat. So this only makes the problem worse. It exacerbates the problem in a way that we can't really control directly, can we? We can't just stop that automatically. It's the temperature that's causing the problem here. There's also great concern as those caps melt, ocean circulation is changing. I'll just hit on one real quick. Maybe you've heard of the Gulf Stream. Ocean Gulf Stream travels up the east coast of the United States, brings warm water up towards northern Europe. That's why much of northern Europe is relatively mild, less cold than it would be. Well, there's great concern, for example, as the glaciers in Greenland are melting and dumping a lot of fresh water in the ocean. If the Gulf Stream were disrupted, that warm water doesn't reach northern Europe's going to get much colder. And you know, of course, these days, what happens somewhere in the world affects the whole world, doesn't it? It's not that we can just ignore that. So that's just another example of the seriousness of the problem. This can lead to other problems. I won't get into social unrest, political conflicts, fighting over water, these kind of things. Earth is changing. Earth is changing. We have a great challenge to try to deal with that, don't we? We can model it these days. Atmospheric scientists are getting quite good at this using supercomputers. Their models have increasingly gotten better and better and better at not only characterizing the problem, but predicting where it's going. You can see a few different colored lines here. If we were to somehow magically turn off all of our CO2, that line could flatten out, but that's not likely to happen, is it? Instead, you see some of the other colors there showing the various outcomes depending how much we reduce our CO2. It is important to remember it's not too late. We can do something. We may not magically be able to turn this off and stop it immediately, but there are things we can do. The world's leaders are trying to do this. You know that annually they meet and they discuss what can be done, how we can do that. Some nations have made some legitimate efforts to move forward and reduce the problem, but it's a big problem. We're all part of it. We all like to heat our homes, drive our cars, do various things. Can we somehow reduce our reliance on those few and eventually eliminate them? So just want to point that out, of course, the fact that Earth is changing. All right. Let's take our last few minutes and address this question. I get this one pretty often. Could there be other Earth-like planets? You see some artist illustrations here. You've probably heard we're finding planets around other stars. By the way, I have a whole lecture on that if you'd like to see it out on YouTube. But it's a fascinating question. What are we finding? Before I dive in, I want to just remind you how special we've seen Earth to be. My students know this, that I harp on that. I emphasize that because I think it's realistic to say that. To say, you know, for a planet to be like Earth in that sense, even be habitable, that's a tall order. There's a lot of things that have to happen. Let's take a look. We'll review just quickly some of the things we mentioned. Number one, a large size. Why? Why can't you have life on a small body? Think back to the difference between the Earth and the moon. The moon's very small. It lost its internal heat. It has no geologic activity. It couldn't even hold on to an atmosphere. Not going to find life there. Earth, on the other hand, large enough, plenty of internal heat, plenty of geologic activity. We know it's at the right distance from the sun for the temperature for liquid water. We also learned that besides having the right atmosphere with that carbon dioxide cycle, Earth has another very important factor that's often overlooked. It has that magnetic field to protect the atmosphere. My students have learned Mars once had a nice atmosphere, and it was eroded away when it lost its magnetic field. The sun's solar wind stripped Mars' atmosphere. They actually calculated how long it took. And so Mars no longer has a significant atmosphere. Earth's atmosphere is protected. So in other words, if we start talking about a planet that's Earth-like, that's another requirement, isn't it? Okay, so we've seen a number of things that would have to happen for a planet to be habitable. Well, I'll give you a quick census here. Some of the latest results. We now know of over 5,000 planets around other stars. That's pretty cool, isn't it? Notice, though, the distribution, most are larger than Earth. Yes, we are finding some about the size of Earth, but there seems to be a relatively small percentage of that. But even so, people always say, well, there's a lot of stars out there. There's millions and millions and millions of stars, and even 4% of a million is a lot, right? Yes, it is. So the good news is there's planets the size of Earth that might eventually prove out to be habitable. The bad news is, of course, it's a small percentage. All right, so how could we then begin to look for a planet, even somewhat like Earth? First, we want to focus on what scientists call the habitable zone. I know I have a lot written here, but I'll just touch on them quickly. The habitable zone, as you see this green region, is where the temperature would allow liquid water, okay? And the reason I want to emphasize this is because when we hear the term habitable, we think, oh, it might have life. Well, it might, but my point is it's only one factor. When scientists talk about the habitable zone, it's really just that first step to say, is the temperature right for liquid water? You've already seen there's a number of other factors, isn't there? Besides temperature, are you at the right distance from a star that, number one, is stable? Because some stars fluctuate in their energy. Number two, are you at the right distance from your star if it's hotter than the sun or cooler than the sun? Number three, is a planet in an orbit that is at least close to circular. Why do I say that? Many of the planets we found do not have orbits that are close to circular. They're more stretched out. They're more elliptical. They get very close to their star. They get very far from their star. That doesn't sound too good, does it? And it's not. So you begin to see that you have to just think a little bit deeper sometimes. Are they the right size? Are they the right temperature? Do they have the right orbit? We talked about the magnetic field and a protective atmosphere as well, obviously, for life to flourish. So I think you begin to get the sense that there's a little more to that question, isn't there? It's not just that a planet might be habitable. Well, it might, but there's a number of factors, and these aren't all of them by any means. There are others as well. Some years ago, NASA launched the Kepler spacecraft. I've touched on this in my other lectures. You can see the objectives here was to go look and see how many planets are there, roughly the size of Earth. What's their distribution of orbits? What's their sizes? What's some of their properties? Kepler is what we call a survey telescope. Go out and find them, send us down the data, we'll dig through it, we'll analyze it, we'll figure it out. And it did a great job for a number of years. It gave us that first good census. Kepler found, I think, roughly 3,500 of those 5,000 planets. We've found some since then. But the point is, it was a first good census. Let's have a look at the results. Again, as I mentioned, maybe 3,500, 4,000 planets. That comes out to roughly 1/2 of all stars have a planet. What does that come out to on average? It comes out to 1 per star. Why 1 per star? Well, some stars don't have planets. Okay, not every star has planets, but many do, and many, of course, have more than one. Look at the third bullet here. About 10% of those stars may have a rocky planet in the habitable zone. That sounds pretty good, doesn't it? 10% of millions? Sure. But again, it's just the first step. I mentioned some have elliptical orbits. Some have even changed their orbits. Maybe they started out well, but they've changed their orbits. Some we find that look kind of promising. Oh, it's this far away, it's this and that. Then we realize it's the type of star that often has huge flares or explosions of energy. That's not a good thing either, is it? So you begin to see, I think, a little bit more about this question, how to think about it intelligently. Since the Kepler mission ended, NASA has replaced it with the TESS satellite, Transiting Exoplanet Satellite. It has not so much done a total survey as Kepler did, but what it's doing is looking more at the more friendly type of planets. In other words, let's focus in on the ones that maybe have the greater potential to be habitable. Masses, sizes, orbits, all those things we just mentioned, okay? And let's particularly look at the ones nearer to Earth that are easier to study. Then we follow up with ground-based telescopes to go analyze them in greater detail. So TESS is hard at work right now. There's a website there if you're interested to go out and see some of the results. Kind of interesting what we're finding. A great variety. Some surprises, some things we did already expect. But NASA and many astronomers are hard at work trying to characterize planets and look for that one that just might be just right. So to finish up, sooner or later, you come to the question about life. And I think the answer is we just don't know yet. First of all, how many Earth-like planets have we found in a habitable zone? You see a number there. It's an early number, 2%. That's a lot, I think. But remember, I've said it more than once, haven't I? It doesn't make them habitable. An Earth-like planet in the habitable zone with a friendly star sounds pretty good. It is pretty good. It's a good first step, but we just don't know. There's still too many unknowns. This one example here, you see Kepler 452. I just selected as one example. The planet you can see is a little bit bigger than Earth, more massive. You're going to weigh more on that planet. It's at almost exactly the same distance from its star as Earth is, and it's orbiting in almost exactly the same amount of time, 385 days. The star is very much like our sun, almost identical to our sun, what we call a G-class star. It's a little bit older. It's about 6 billion years old instead of 4.5. But we think what's special about Kepler 452b is that the planet shows no signs of orbital changes over its life, so that means it's been in a stable orbit. Could life have developed there? We don't know. But there's your example of what we might call a good chance of a friendly, habitable planet. So time will tell. Some scientists are more optimistic. Some are more pessimistic. I try to be realistic. Show me the evidence. Nature always seems to surprise us, doesn't it? But I will caution you that someday as you hear different announcements, give them time to pan out. Give scientists, give astronomers time to be clear, to be sure. It's very difficult to study these planets, not only at their great distances, but because we get very little, if any, light from them. Often we're studying just the effects on their stars. So you can see my other lecture here on extrasolar planets. I'll make a quick plug if you want to go out to YouTube and check that one out. More details on this question. So what do you think? As usual, thank you very much. As usual, I try to give you as much information as I can in an hour. Would you agree with me? Earth truly is a magnificent planet, and we really should try to take better care of it. You know, I often find that most anybody I talk to, we all agree on that, and we can only act in large numbers. Everyone has the right intentions, but we also have a modern society that we live in, and so it's very difficult for us to make those changes, but I think we can begin to do that. So again, hope you've enjoyed our presentation. Before I take questions, just want to make one more plug for those YouTube videos. Lots of different topics out there. I talked to a few of you before and weren't aware of that. Just want you to know there's lots of different, more than you see here. The one I did recently on the story of our solar system on Zoom gives you a lot more of this type of information if you're interested more in Earth and the solar system. I think you'd like that one. There's one here on the outer solar system. You can see on the spacecraft that went out to Saturn. Again, a number of different ones, so I invite you to go on out there. And also, I'll just remind you, a lot of you know this already, for those of you that are just simply not able to take college courses here, I've made a few small college courses for you. Okay, you can watch them on YouTube. One on solar system astronomy, one on stars and galaxies. These are short lectures, 20, 30 minutes at a crack. I think there's 12 of each. You can get kind of a short course in these areas and get a nice, simple introduction. Okay? So with that, got to make you laugh once. It's that time. We're going to pass around some microphones here. It's your chance to speak up and ask me what you would like to know. We'll start down here with a familiar face.
That early blip in 1940, 2 years. Was that World War II?
You caught that, didn't you? This gentleman's wearing a hat that says World War II veteran.
I didn't get those 2 years.
So you were only just this tiny little part of the problem. Don't worry about it. It's okay. You just those 2 years. Yeah, there was tremendous emission. You can imagine the world's militaries went to work, didn't they? Okay. Dr. Caputo, please. Our college president's here with us tonight. Thank you for joining us.
Professor DalSanto, forgive me if I butcher this question. I'm an accountant by trade, so this might be
okay.
far beyond me. A lot of the second half of your lecture, you talked about the effects that are kind of heating things up on Earth. Earlier on in the lecture, you talk about how planets can cool down. Is that a danger for Earth, cooling down? Is it going dead? I imagine it would take millions upon millions of years, but is that a possibility?
That's a good question. I believe you're saying the internal heat, is it going
Right.
to lose that and run out? And no. Good question. Short answer is no. Earth is stocked with so much internal elements that are radioactive. Somewhere I read an estimate once, it could go on for billions of years, so we're good. But thanks for checking in on that. That is an important one, right? There's one way over here in the corner, please.
You emphasized Earth's magnetic field. Is it true that it has flipped over time?
I should ask one of my students to answer that. They just covered that. Yes, it is true. Yes, it is true. I've got a graph somewhere that would show you that.
The question is why? And the second part of that is, was the Earth then left naked for a period of time with no
Yeah.
magnetic field?
So the short answer to that would be that yes, it has basically flipped polarities. In other words, if you were holding a compass, you'd see the needle do this. Now that takes time, doesn't happen overnight. It's due to motions deep within the Earth, again, essentially doing this kind of thing. I'm just crudely trying to give you some idea. It's the net effect. I had a discussion once with a scientist on that, and he kept emphasizing that to me. He said, tell your students it's the net effect. We have lots of different motions deep within the Earth. What does the net turn out to be? It turned out to be this. It has flipped a number of times in the last 10, 20 million years. Life has dealt with it. It's a relatively short time in which it flips. There's been some hints. Some were kind of wondering. A few years ago, I read an article like, could Earth be getting ready to flip again? Hasn't panned out, but it could happen. Thank you. Who else wants to try? There's a hand over here.
Yes, those satellites that are taking surveys of stars and their planets, I'm assuming that's just in the Milky Way galaxy.
Yes.
So there are other galaxies which potentially
Yes, so maybe partly where you're going there is, well, we have now surveyed, and I should emphasize this, we've surveyed kind of a local region of space. We're only able to look out so far because we're measuring very delicate measurements of stars. There's very few planets around other stars that we can actually see. We've only got, I want to say, a dozen or 18 pictures or something like that. But we're carefully measuring the effect of the planet on the star. We're looking at the star saying, the star has this property. So it's somewhat indirect. And so that means we can only look out so far. There's not any run number, but only several thousand light years. Well, the Milky Way itself is a lot bigger than that, and then you have whole other galaxies. You're right, that there could be that many more planets out there as well. Yeah, good question. Is there one here somewhere? I think I see a hand. Sure.
So I guess there's two additional things about having more life on Earth. One is that the Earth's tilt that causes seasons. That's a very important driver of life. And also then the presence of the moon that stabilizes that tilt.
Yes.
It's also important. So
Yes. So that's a good point. In other words, what this gentleman's bringing out is the Earth's tilt has not changed very much over its entire history. Other planets we think have. We have evidence on Mars that its tilt may have changed significantly. Why has Earth not changed so much? The moon has a stabilizing effect. If the Earth tries to do that, the moon says, no, it's going to pull you back here. You shouldn't really do that. That's not good. And it keeps it in a very level. Nice. Now, there has been a few degrees here and there that have had some effect, but you're right. Not a huge effect there. Okay, in the back here.
So you showed the graph of the carbon cycle as it correlates to temperature and the spike in the carbon. Do we anticipate now that fast descent, right? Because again, it's a cycle, right?
Back about here, right there.
Yes. So that's such an awesome graph. And as we look at that, do we expect it to then
I think I followed the question.
come back down again?
You're starting to see it come down there.
Exactly.
That's a long term, and unfortunately, this graph, of course, 500,000 years, even that downward trend is several thousand years.
Absolutely.
Yeah.
But as you look at best fit lines and statistical modeling going out.
Yeah, so I think the short answer to your question is this is going to overwhelm that. That might be the right word for it. It's going to overwhelm that. Normally, the Earth might have started kind of doing this. Like, oh, no, you don't. The humans are at it. So good question, yeah, because again, I think I follow you here that normally, statistically, you might say, it's almost time for a downward trend. Well, apparently not, yeah. Okay, good. What else? we think? I see a hand somewhere. Sure, thank you.
Just a question, one of your slides you had O3 or ozone.
Yeah.
I'm just curious with the ozone layer where that's at today and fluorocarbons and,
Where'd that go? I had it on there somewhere.
yeah.
Anyway, ozone layer, yeah. So ozone is a special form of oxygen. Oxygen normally is two atoms bound together, O2, you and me breathe that. But in the upper atmosphere, the sunlight can come in, the ultraviolet light can break those molecules apart, and what you end up getting is you get a free one, and it kind of wants to stick to a pair over here, and you get now O3. It's ozone. Some of you older ones can remember years ago we had a little bit of a problem with that, right? The ozone layer was being depleted because we were generating chemicals that broke it apart. Why do we need that? That ozone layer you could think of as yet another specific part of the atmosphere's protective layers. It would help shield us from ultraviolet light. As that began to break down over the polar regions in particular, I'll never forget reading an article back then about 20 years ago, down in far southern South America where they graze cattle, they said the cattle were all getting cancer from the ultraviolet light. So it was just I won't say a small, but it was a small effect. But the good news is we realized it and we did something about it. Now granted, it's a far smaller problem than we face today, but the point is we did something about it. Okay, so I hope that answered your question on O3. Is ozone. It's a special form. Gradually, very slowly, this has been slowly kind of healing itself, but we did a lot of damage. Yeah, there was, you call it the hole in the ozone layer. Remember that, some of you? Okay, did that answer your question, sir? Okay, very good. Who else? There's one. Second row here. I better get ready for this one. Good friend of mine.
I just want to make sure that I understood a statement you made earlier about when you're talking with subduction and how the tectonic plates are being lubricated by the water underneath them, and you mentioned about percolation of the water through the rocks. So I know that when the Earth was originally forming, and besides all that dust and gas, there was a lot of ice debris, in which most of that it was and still is under the ground. And by the time the continents cooled after early in the Hadean, then you had the late heavy bombardment, which brought some more water via the meteorites. And one of those are going to be ones having heavier oxygen, the other lighter oxygen, which is that we know that one is older than the other. The question is there today any interaction between those two different waters or ages of water? Like the younger waters, what's on the surface now, mostly brought by the meteors, and stuff under the ground is mostly what was old when the Earth was forming. Is there an actual percolation or an interchange, an exchange between these two water sources? Though technically, I guess the one underneath would not be water. It's more like greenwood-like minerals and whatnot. But
so while I don't have a lot of detail on that, it is an interesting question that I will look into. My understanding of it is there's not a huge dramatic difference and change there. Because of Earth's geologic age, of course, there's obviously been a lot of, what's the right word, interaction. So now I got homework. Thanks a lot. No, it's a good question, interesting question. He mentioned a couple of things there that I didn't get to talk about here, how, yeah, there was kind of early water, then we think later on even some external water might have come to Earth from comets. Although I will touch quickly on that. We wanted to test that hypothesis, 15 years ago. People were saying, yeah, where did Earth get its water? Was it all from volcanism? Or maybe it was comets that crashed into Earth. How could you tell? Compare Earth's water to comet water. So they flew a spacecraft out the comet. They analyzed the ice. What do you think they found? No. And that was a surprise. Most people said, oh, yeah, sure, we're going to figure out, yeah, that's the water. And it's like, oh, maybe not. Now, we haven't ruled that out, that comets brought Earth some water. That could still be very possible. There's, but it doesn't appear that that's the major source, and that's why we've kind of gone a little bit backwards now to saying, well, it's probably then the volcanism. So I'll look into that a little deeper. But for now, my understanding is no, there's not a huge effect there. Okay? Another question here. I see someone. There it is.
I
Yes,
had a
sir.
question. Can we throw the Earth out of climate?
Yeah, so can we throw the Earth
Can we throw the Earth out of the stable climate cycle?
Yeah, there's a lot of concern about that question. It's called the tipping point. Have you heard this? Are we at a tipping point? In other words, could we push the Earth so far that it starts to kind of run away and then we can't stop it? And I think the right answer there is we shouldn't try. We shouldn't find out. Don't you think? Obviously, it makes sense, and I think everybody in this room wants to do the right thing. But we don't know exactly where those tipping points, and there's more than one. There's kind of the big overall global one. Do we get the Earth too hot? Sure, you know. But there's other ones. Do we mess with the oceans this much that we've now disrupted the currents? Do we do this? Do we do this? Do we do this? There's multiple tipping points. The big one, of course, temperature. Okay, so we don't know yet. It certainly seems likely that sooner or later there is that point, right? Sooner or later, but we don't want to go near that. And that's what a lot of people are saying is let's not find out. That's the point. By definition, it's like now it's too late. It's going to run away. As it is now, you've probably heard some of this. Even if we somehow dramatically made a change, there's still going to be effect for decades to come. So I hate to be negative here, but some of you younger people in this audience, you're going to see some of this for decades to come. Whether, you know, sure, we can kind of deal with that. Sure, we live in an affluent country. But, you know, you get these droughts. You know, I've been kind of following a little bit what's been going on in these western states with the Colorado River. These lakes are down to their record lows. They're they're going to have to turn dams off from generating power. They're down to like 30% of what they used to be. It's like, wow, what do you... And I can't blame the authorities. There's no simple answer. Who wants to stop using water? It's like, well, we need water for this and for this and for this. You know, the western United States makes a lot of food. Agricultural use out there. You think of California. I mean, anyway, I can go on and on. There's no one simple answer, you know, but there are some answers that we can all at least begin, okay? Other questions? Had some good ones. Had some good ones. Yeah, no? All right. Well, if not, I will again thank you. I will tell you I'll stick around for a few minutes. Thank you very much.